Hi, and welcome to Geeks for Geeks. Today, we would be discussing the problem named as IPL Match 2021 Match Day 2. So, in this problem, we need to find the maximum element in all subarrays of size k. So, you would be given a size k, and suppose the number of elements, suppose the size k is 3. The number of elements in this would be this, and the maximum element in 1 to 3 is 3. That is why the output to the first is 3. Then we have the next set of numbers, that is 2, 3, 1. And again, the maximum number out of 231 is again 3. That is why the output to this is again 3. So let's move to the next one. Then it is 314. The maximum element in 314 is 4. That is why the output to this is 4 itself. Okay. Then we have 145. This time the maximum element is 5. So we can say that we just have 5 here. Then we have 4, 5. The maximum element is again 5. So that is why the output of this is 5 itself. Then we have 5, 2, 3. The maximum element out of this is again 5. So that is why the output of this is 5 itself. Then we have the last set of numbers, that is 2, 3, 6. And the maximum element out of this is 6 itself. Okay. So you would be given a size k, and you just need to iterate over that, find the maximum element, then you need to go over the next set of elements, and you need to do that. So if you analyze this test case only, it would give you a hint that the difference between the first subarray and the next set of subarray is just one element subtraction and one element addition. What I'm trying to say is that the first subarray is this and the next subarray is this. So you can see that the first element is going out and the next element is coming in. This is there. Then you can see that suppose that is 231, and this would be valid for all the subarrays. Then we have the next set of elements as 314. Okay. So we can see that this is a kind of sliding window approach that we need to do. But the problem is that we can't really find the maximum element. Why we can't really find the maximum element? See, in this problem, it is very easy in this test case itself. See, we have 1, 2, 3, then we have 2, 3, 1. So the maximum, so we would just find the maximum element out of 1, 2, 3, and the maximum element would be 3. Okay. So next time when we go out, that is to the next set of numbers, so we just see that we are taking out 1. So we see that the maximum element is 1 or not. No, it is not. So we would simply remove 1. Okay. The maximum element is not problematic here. In the next set, again 1 comes in, and we can see that it is not able to replace the maximum number now, because see, again this time also 1 number came. So the ordering of the number does not matter. If you observe, only the numbers is mattering. Okay. So we can see that if the elements we are trying to take out is interfering with the maximum element, then it is not okay, but it is okay when the new element is less. What I am trying to say is, अगर नया एलिमेंट जो एलिमेंट जाने वाला है, अगर वो मैक्सिमम एलिमेंट को छेड़छाड़ नहीं करता है, तो वो एलिमेंट वैसे का वैसे ही रह जाए. जैसे हमने देखा कि we have 1, 2, 3. Okay, we have 1, 2, 3. Then we are taking out the maximum element, it won't interfere the maximum element. But when it is 3, 2, 1 and the new number is suppose 4, okay, so we can see that if we remove some, in this time we have calculated the maximum number is 3. So now if we want to remove this 3, then we can't take the second maximum. If you observe that after we remove this 3, see, after we remove this 3 and we remove this 3, we can see that we can't really get the next maximum. Okay, we can't really get the next maximum. So we need a way to get the next maximum also. Like if the first maximum is taken now, we should be able to get the next maximum. Okay, fair enough. So this would be problematic in scenarios like 7, 5, 2, and then we have again 1. So the problem would arise when we have k is equals to 3. Here for all the explanation k would be 3. So the first for we have found out that k, the maximum element mx is equals to 7. Okay. As we move forward, we need to take out this 7, then we should be hitting upon now 5. And now to find out the maximum element, we again need to iterate. So this is telling us to go to the first brute force approach, that is individually constituting the maximum element by using two nested loops. So what we can do is we can iterate over all the window of size k. So we would first iterate from 1 to k, then we would iterate from 1 to k plus 1, then we would iterate from 1 to k plus 2, then we would iterate from 3 to k plus 3, and this is taken into consideration that we would go from 0 till less than k, 0 till 1 till less than k plus 1. This is what is taken into consideration. If you just want me to convey, I would just tell you, see, just let us take the sample test case only. That would be more feasible. Okay, fair enough. So now, if you just observe the things, that 0 till less than k. So k is equals to 3. This is 0, this is 1, this is 2, this is 3, this is 4, 5, 6, 7, 8. So if we go from 0 till less than k, so 0 till the value 2, the output to this would be 3. Then we would go from 1 to less than k plus 1. K plus 1 is what? K plus 1 is 4. So 1 to less than 4. So 1 to less than 4, less than 4. That would be 2, 3, 1. Again, 3 would be there. So as we have already taken out, this is how we would proceed. So for each index, we are doing k operation. So from 0th index, we are just iterating k elements. From 1 index, we are just iterating k index. For 2 index, we are just iterating 1. So we can say that for one element, we are doing k operation. Okay, because finding the maximum is just a matter of constant operation. Okay, so we just update the value if we see a better value. That is simple. Suppose we have 5 and then we saw 6, so we would just update it to 6. Okay, and the compare and the equations that less than greater than is equal to is constant. So comparison one. So we can see that for one element we're doing k operation. So for n element we would be doing n into k operation. That is n multiplied by k. So can we do better than this or not? Yes, we can do better than this. So we can see that we need to find a way where we can store the second maximum or the third maximum, and we can also delete accordingly. How can we? So now the problem is find maximum in sliding window. So we need to find the maximum in sliding window at each iteration in, let's say, constant time. Okay, we can do this. So how can we do this? So thinking about this approach, we can say that if we just store them in the sorted manner, because see, whenever we require the first largest, second largest, third largest at each point of time, the first thing that should hit in your mind is the intuition. The intuition is very important. The solution is not very important. Let's talk about the intuition. Okay, so the intuition that we want the first maximum, then the next maximum, then the third maximum. So if we want maximum at each step, if you follow my videos, you would be already knowing this, that if you want maximum at each step, this tells us that we need a sorting thing. Okay, we need a sorted order. Either you sort it or you do it through a data structure. Okay, so this is something, because after, see, we after 5 then we need to go to 4, so we need to store the next element also, the next smaller element. So how can we do this? Let us try to think. So we can think that instead of taking all the elements and then sorting, so we would take k elements and then sort it. We would again take k elements and then sort it. So instead of taking k elements and then sorting it, which would be very costly, we can just store it in the sorted manner. What I'm trying to say is, let us just try to see from the sample test case. Okay, so let us just try to see. So we would maintain a sorted order kind of thing. Can we do this? Let us try to see. So suppose we have 1, 2, 3. So first we would go to 1 and we would store it in somewhere. Let's take a data structure X. Okay. Then we have the next data structure, next element. That is what? The next element is 2. So does the sorting order is maintained? No, the sorting order is not maintained. We need a sorted order. So what we can do is we can just remove this one because it is less than 2, and we can keep here 2 because we need a sorted order. Then we come across 3. Okay, then we come across 3 and 2 and 3, but we want 3 and 2. So let's remove this also, 2, and let's keep it to 3. Okay. So after processing k elements, we would say that yes, that is the out. Then we have the next set of element, that is 1. So first we would check that the elements in the data structure X, it is on the outside or not. Now how would we know that 3 is on the outside or not? So what we can do is we can store the indices of to know if that element is out of this range or not. Just try to think, just try to be with me. Okay, so this is index 0, this is index 1, this is index 2, this is index 3, index 4, this is index 5, this is index 7 and 8. So how would we know if the current element in the DQ is outside the element that we have already kept up? मतलब जो एलिमेंट चला गया है उसमें से ये एलिमेंट बिलोंग नहीं कर रहा सॉर्टेड वाला, ये कैसे पता चलेगा? We can just store the indexes. So now what we would do is we would store the same thing. This time we would store 3 with the index. So instead of this time we would store the indices. So now we would store the indices 2 and the value is, so I would just have it here. So I would just write index and this is the element. We would just store the element, we would just store the index, but for simplicity here I'm also showing you the element so that I don't create any confusion. Okay, so up till now we found out that we would store 3 and the indices is 2. So now we know that we need to kick out the value 0. So 0 is not the indices that is there. So we won't do anything. Next we would come to 1. So now we have 1. So we want a sorted order. So we want, even if we just insert 1, we want the ordering as 1, 3. Okay. So we want the ordering as 1, 3, not 3, 1. Okay. So now can we think of, please cut this part here, which was the ordering thing. Okay. Now this time. Okay. So now we can see that if we insert 1 with the index 3, the sorted order is maintained. That is, we are going from high to low. This is the sorted order we are trying to find. Okay. Then we would say that yes, 3 is our first element because the first element standing at this position would be the maximum element. Okay. Then we go to 4. Okay. This time we would again see that the element we are trying to kick out is the index 1. So index 1 is out of this range or not? Yes, index 1 is not in this range. So we won't do anything. We want to insert the value 4. Now this time we already have 3, 1. And if we insert 4 at the end, we can see that there would be a problem that is encountered. That is, the sorted order is not maintained. So first we would remove this one. And then we would see 4 is greater than 3 or not. Okay. Yes, it is. So we would again remove this one. And this time we would now insert 4 with the index as 4. Okay. And then we would say, yes, the largest value is 4 itself. Okay. Then the next value is 3, 4, 5. So we want to kick out the index 2. So 2 is not present. So we would not do anything and we would simply move forward to the next one. So now we have 1, 4, 5. Now we want to include 5. But if we include 5, that would be 4, 5. But we want 5, 4. That is not possible. So now we would remove this 4, 5. and we would insert 5 with the index as 5. In the next iteration, we want 4, 5, 6. So we first need to remove the index 3. 3 is not present, we won't do anything. Then we have 4, 5, 6. So now this time 6. So we want the ordering as what? We want the ordering as 5, 2. And that is can be done. So we would just insert 2 with the index as 6. Okay. And then we want 4, 5, 7. Okay. Then we want 4, 5, 7. Then I want this one 5, 6, 7. Okay. So now we have to insert 3. Okay, 3 is not there. So what we would do is we would remove this value and we would say 3 and 7. Why? Because the ordering is mentioned. See the element side 5 and 3. Okay. Next, we want to insert the value 6, 5, 7. So at this point of time, we can see that the element we are trying to find is the element 6. So we would remove everything and we would say 6 and the value is 8. And then we would report accordingly. So every time finding the maximum element is now not an issue because the first element would find the maximum and we would maintain the sorted order. Now, for simplicity of this thing, let us see how this is working. So now let us take this example. So we have k is equals to 3 and we would do the same thing and we would see how it is working. But before that, let me first discuss, okay, which data structure can be used. So we want insertion at back, insertion at the back. Okay. Now if the last element is less, we want to see the last element. Okay. So we need to peek the back element. And then we need to remove the back element also. Remove back element also. Next thing is that we need to report the first element. So peek first. Okay, peek front. So we need to peek the front element. We need to insert from the back. We need to remove from the back also. So we can see that if we want the peek or remove from front as well as back, the only data structure that is most suitable is the doubly ended queue. That is DQ. That is why, according to these all requirements, DQ is the most appropriate one. So now let us see how DQ can be used to solve this using the same thing that we have seen. Here k is equals to 3 for all this arrays. So now we would just simply process. So for 1 to 3, we can see that we would store 3 because we need a sorted ordering. First it would be 1. Okay, first it would be 1. Then we would come and say 2 is greater than that. So we would remove 1. Then we would keep 2. Then 3 is coming. So we would say 3 is greater than 2. So we would remove this one and then we have 3. Okay. Then see how 3 is being maintained. Then after that we are removing 1, but 1 is not present. So next time new 1 is coming and see after that we would keep 3 and 1. This is how the DQ would look at the end. In the same way, here also 3 would be first stored and then we have 4. So this time 3 and 4 is not there. So we would now remove 3 and then we would keep 4. So see how 4 is taking in the first part. So now here also let us see the different kind of arrays. Here we can see the maximum element that we would store is 7, 5 and 3. We would maintain the sorted order. But now when 6 is coming in, first we would remove the last element. Then again we would check for the last element. Now 5 is also less than 6. We would remove 5 also. Now 7 is greater than 6. So we would now insert 6 in the sorted order. See how we are maintaining the sorted order. Next we have 753. Again we would have the same ordering, that is 753, and then we would insert 2 because it is less than. So it is already in the sorted order. Okay, fair enough. This is how we would proceed to have this. So now the algorithm is very much simple. We would first iterate over the k elements and we would keep them in the sorted order. And then we would insert the value in the answer. For each subsequent, we would report the first front element and we would report. Okay, so now let us move to the implementation. So now what we would do is we would first build out a vector of in the answer to store that simply. And then we know that we need a DQ. So we would initialize a DQ also and we would name it as DQ. And then we would process the first K element. So for int I is equals to 0, I is less than K and I plus plus. We would do that. Next, we would check first that see before accessing the last element in the stack or DQ, we first check if the last element with the stack is containing some elements or not. Else you would find an error. That suppose there is no elements, then in that scenario, you would be checking the last element and then you would be falling into an error. So now let us move forward and we would see that DQ shouldn't be the empty element. Okay. And we need to maintain the sorted ordering. So let us first see. So when would we require to remove elements? We would require to remove elements. Suppose we have one and we want to insert two. So in this scenario, the last element, if it is less than or equal to the current element, we would remove that element. This is what we can say that if a of dq dot back, because we are storing the indices, please remember this, is less than equal to the current element, what we would do is dq dot pop back. Okay, dq dot pop back. And after all this is done, we would have an element which is greater than that. So let me just show you what I'm trying to say is that suppose we have 5, 3, 2, and then we have here 4. So 2 would be removed, 3 would be removed, but after 5 it would be 4. So now we would be having an element at dq either empty or the dq would contain an element which is greater than the current element. So now it is appropriate enough to now push this current element. So we can say that dq dot push back the current indices. Okay. So now this is done. After that, we have processed the k elements. So for the first k elements, we have the answer. So now let us push this answer. Okay. We would push the element. So we would say dq dot front, because front would be containing the largest, because we are maintaining a sorted order in the reverse. So it would contain the largest one. Then we would process the rest of the elements and we would say for int I is equals to k. Then we would say I is less than n, and then we would say I plus. Okay. And this first we would need to remove the elements which are outside the range of this window. So what we can say is, suppose we have 1, 2, 3, 4, and the indices are 0, 1, 2, 3. Okay. Suppose we are at this index and we need to remove this part. So we can say that if, see this, and k is equals to 3, same for all expression as I said. So if we can say that current index minus k, if the element that is there is less than equal to current index minus k, that is current index is equal to 3, 3 minus 3 is equals to 0. If it is less than equal to I minus k, we would remove. So now we would say that first we would check the last dq is empty or not, as I tell you. So while dq is equals to empty, not empty. If the dq contains some element, then we would move forward and we would say dq dot front. dq dot front. If it is less than equal to I minus k, then what we would do is dq dot pop the front element. Now the front element are popped. Then we would do the same thing we were doing here. Okay, same thing. Then after that, we would again have the answer for this window. So now we would again push the same thing. Okay, then we would return that. So just compile and run and see how many mistakes are we making. Okay, yeah. Okay, the expected output and our output is very same. Let us try to submit this and see. And yes, we got an AC. Now let us talk about the time complexity of this problem. The time complexity of this problem is very easy. At each element, we are doing how many operations? So see, each element would be inserted once in the DQ and each element would be taken out once in the DQ. So in DQ, we are total doing how many operation? 2 into n. Okay. And for each, we are, it seems that it can be many elements that we are taking out. But each element can be inserted once and can be taken out once. Okay. So by this, we can say that the time complexity of this problem is bigger than ignoring the constant 2. And the space complexity is that at all times, we would be storing roughly k elements. Okay. So we can say that the space complexity is big O of k. Let us see the intended time complexity. Okay, intended time complexity is not given here. So, if you were here till this point of the solution and you found it worthy enough, consider commenting on the video and liking on the video to give this video a better reach. Thank you and have a nice day.